Hi guys, I'm back. Chapter 15 review, part duo. All right, so here we go. We left off with field. So electric field again is the area that the charge of a point charge or an object affects the area around it. Okay, so electric field, capital E, it is a vector. If you remember, the test charge is a small charge, meaning it has a very small size, but the actual charge amount doesn't actually matter because it cancels out. Okay, they use 1 coulomb because it does cancel. Okay, the test charge for our purposes does not create its own field. Okay, we're just using it to examine the field that already exists. Okay. All right, there's that review question with the answer. All right. So again, you have to use your own brain to figure out the direction. If I have a positive object, okay, and this Q naught thing is the test charge. If I drag the positive test charge over here, the field is going to push it away, okay, because both are positive. If I have a negative object right here, okay, and I bring a positive test charge here, the field is going to pull it in this direction because opposite charges attract. Okay. Again, a lot like electric force, when we're doing fields, we use superposition. So you're just adding the vectors. So you're breaking them into their components and then adding them together. So again, the same problem-solving strategies we've been using all year. Draw yourself a picture, label everything out, break everything down into their components, find the force, okay, and make sure that you get the right direction and angle, okay. Add all the x and the y components, and then use the formulas to find the resultant and the resultant angle, okay. Then you have electric fields. So assume that you bring a point charge into that area, then you can then figure out, because you know the forces, what the field is at that point. Okay, those are the problems for 15.4 that we already did. If you want me to do any of them, just leave me a little comment and I will be more than happy to. Okay, then we started electric field lines. So these just kind of help us figure out the direction of the field around a point charge. So again, it's a capital E, it's a vector. And if you remember, the number of lines per unit area, oh gosh, what's going on there? The number of lines that you draw out of a charge is kind of proportional to the strength of the field. And if you remember, it always has to be perpendicular to the surface. Okay? That will come into more importance next chapter. Okay, electric field pattern. So here's a basic positive charge. Notice that the arrows are going outward. And here's a basic negative charge. Notice that they're coming inward. And we did that worksheet where you drew all those bizarre combinations, including capacitors or parallel plates. Okay. It always goes from positive to negative. Okay. And again, the number of lines is proportional to the charge. So if you have one charge that's a lot stronger than the other, there needs to be a lot more lines coming out of that charge. And field lines cannot cross. Those are just kind of the rules. If I have a positive and a negative, that's what it looks like. Notice they're going from the positive to the negative. Okay, so if I placed a point charge anywhere, say here, okay, it would be pulled towards the negative. If I put a point charge here, it would be moving outward. Oh, it won't let me do it. Okay. Things get really interesting if you bring two positive charges next to each other. In the middle, we have this thing called an asymptote. Okay, which is an area that has actually no field. So if I put a point charge at C, it wouldn't actually move. It would be suspended between the fields. Okay, and there's a sample question there. Again, we did some of these on the worksheet. Notice how there's twice as many lines coming out of the plus 2Q and less lines for the minus Q. The field lines don't actually exist, but they're just there to help us figure out what's going on. There's a review question, a couple of them, I think. Sorry, it's slow. All right, so when I am in electrostatic equilibrium, okay, meaning that there is no net force, okay, like that point C that I was just talking about, the object is in electrostatic equilibrium, okay? The electric field is zero everywhere inside. So if we're looking at like a Van de Graaff generator, the electric field extends from the surface of the ball, not inside of it, okay? Any charge on a conductor is all on its surface, which is what I just said about the Van de Graaff, okay? And again, the field is always perpendicular to the surface. On an irregularly shaped object, it accumulates at places where there's like a point, and there's a slide here that'll explain it. So if I have something like this, I will have charge accumulate here and accumulate over here, okay? Where flatter areas like this don't really accumulate charge. And if you remember when the Walter Lewin lecture had that huge Van de Graaff and he put all those paper things on it and turned it on, it moved out in perpendicular lines tangent to the surface, okay? I just explained that. There's some reasons why that has to be true. There's that. Okay. I think there's a slide down here. Yeah, here we go. So if I have an object, the charge is just kind of forced because of the shape into the points. Okay. Faraday has a very famous ice pail experiment. You can go Google it, read it. It's just the kind of famous one that explains this. So there's your questions for 15.5 and 15.6. If you want me to do any of them, let me know. And then this Millikan oil drop experiment is also a very fundamental experiment. It used two parallel plates with a battery attached, so that's a capacitor, okay? Dropped charges through here, okay, to see what ended up happening. And this experiment measured what the elementary charge of was. Like, and that's how we got that Q equals NE equation that we were using, okay? Also proved that every electron is the same, okay? Here is the slide explaining how Van de Graaff works. So that's the thing we were all looking at. There's a belt inside here that is made of rubber. So obviously you can see here how it ends up with a positive charge. Okay, so because of that, it pulls the negative charge off of the outside of the dome, making the dome positive. And there's a problem for 15.8. All right, so that's chapter 15. Quick review of where we left off right before the break. See you guys soon, I hope.